Okay, this video is going to be for lessons sections 4.3 and 4.4. So it's kind of long. I'll present my notes here for you guys to write down as we go along. So we're going to be looking at the exponential function. So we looked at geometric sequences, what kind of act like an exponential function. They have a lot of the same characteristics and things like that. And so now we're going to look at the exponential function itself. So an exponential function is a function of the form y equals a times b to the x, where a is a non-zero real number and b is a positive real number, and b cannot equal 1. So we're going to be using this equation format for many real-world problems. So the a number that you see in the front here is what's called the initial value or the start value for many problems that you do in real life. Because if the exponent is 0, usually at the start of something, the value would be 0 for the exponent, and then b to the 0 power is 1, so you just end up with whatever that a number is as your starting value. The a also becomes, because x would be 0, a also represents the y-intercept of a graph that might come up. We talked about the common ratio in geometric sequences, and so the b number here, the base number, would be that common ratio. So, some things about it that we want to look at. An exponential function is related or similar to the geometric sequence, which was already stated. So let's compare the geometric sequence to the exponential function. What is similarities? What is slight differences and things like that? So I laid out a couple things here for you to kind of walk you through. So I gave a sequence, 1, 3, 9, 27, 81. Pretty common one, we've all seen it before. We put this into a table. N is the number in the sequence, a sub n is the value in the sequence. We find that it has a common ratio by doing the 3, because just times 3 each time. Over here, in a function table, we have x and y, so f of x is another value name for y. Do exactly the same thing, put it into a table, and you see that the common ratio, in this case, which would be the b value, is also going to be 3. So the common ratio is 3 over here in the sequence, and the base number is 3 over here. It's the same number. In writing the explicit rule over here, we use a sub n is the start number and the common ratio n minus 1. Okay. Oh, I forgot to mention over here, in function table format, this one started at 1, this one starts at 0. So that's one of the slight differences that we have over here. Because to get the value of 1, the x value has to be 0. See, if you look at the exponents over here, this is n minus 1, and then this one right here is just x, because we had just to the x power up here. We're trying to fit into that mold. And so this one has to start at 0 to get that start value to be a 1. So that's the slight difference over here. A function table can start with any number in its domain. So I could have started anywhere. If I can start at 0, it makes it a lot easier to do. And the sequence starts with the term 1. So this one always starts at 1. So an exponential function rule is similar to the sequence rule for any term. The sequence rule for any value is a sub k, the common ratio r to the n minus k. And if k is 0, then I literally just have the function notation format. So very similar, same process we're going to do that we learned in the geometric sequence format. How do I find an exponential function? What is my process I want to follow? Well, if you have numbers, put it into a table. Whatever format they give you, put it into a table. Find the common ratio, which is going to be the base number, b. And then try and find the 0 term. If I find the 0 term, that's that a sub 0 right here. So that 0 term is the number that goes right here. Okay? If you can't find it, I can use this format right here and pick any point. Just remember to whatever the place it is in the x, wherever it is over here, that I use the proper k value. So like right here, if I wanted to use 2 and 9, 2 and 9, then this would be 9, and this would be n minus 2. And that will produce, and then we can get it into a format that fits this. We'll do that at a later time. For right now, just find the 0 term and plug it into this formula, and you should be fine. So here's an example. Let me move that out of the way. So I gave some numbers right here. I'll write it a little bit bigger so you can see it. So we're going to write the exponential function that goes through these points right here. And to do that, we want to put it into a table. So let me go ahead and do that. I'll move off to the side and I'll put it into a table so you can see these numbers in a table format. So here's the x, here's the f of x, or the y. We have 0, 1, 2, 3, and 4. This is 27, 81, 243, 729, and this one over here is 2187. So we put it into a table. We want to find the common ratio. To find the common ratio again, or the b value, we just simply need to take two numbers, consecutive terms, and divide them. 27 over 81, and I get a number. Take 81 over 243, confirm that it is indeed true, and you will find that I'm going to basically divide by 3 each time. So my common ratio is 1/3. So once I have that, then I can take the common ratio b. Okay, that's my base number, excuse me. And this is my start number. So I just need to put it into that format, which is y equals a times b to the x. Plug in this number is a, that number is b, and we get the equation for this table as 2187 times 1/3 to the x. And that's how that works. Okay, so that's how you can use and find an exponential function from a table, provided you have a start value and you have the common ratio. So let's look at some of the graphs of these things. We have two basic parent function types. Okay, exponential growth and decay graphs or functions. There's a lot in here. I'm going to kind of walk you through it real quick. Okay, so a growth function, here's my standard form for an exponential function. There's a times b to the x. A has to be positive, and b has to be bigger than 1. So the base number has to be bigger than 1. If that occurs, then I have a graph that looks like this. This is a growth function. And it will go through the y-intercept right here is 0, comma, a. So from that equation right there, if the x is 0, e to the 0 is 1, 1 times a is a. So it always goes through, that's the y-intercept. Now, in real life problems, they sometimes give you information in the terms of a growth rate. So if I use this for population growth of some type, then this equation modifies a little bit to this equation right here. It looks very similar, but the base number is going to change a little bit. And the base number becomes 1 plus r, where r is called the growth rate. So they'll say the population is growing by 2% per year. So that means the r becomes at 2%. And then we would make it into a decimal to plug into this formula over here. Thereby, if you look at it, b has to be bigger than 1, so the r is going to guarantee that this number is going to be bigger than 1. So r is called the growth rate. 1 plus r is called the growth factor, just so you know. 1 plus r, that whole base number is called the growth factor. This is the terminology that they use. Over here, a decay function looks like this. Has a lot of the same characteristics as you will notice. Here's the formula again. A is greater than 0, so that's to be positive, and b is between 0 and 1. So now this b number is less than 1, usually a smaller fraction or a decimal or something like that. And so remember, that's a decay. Same process here. What if a population is decreasing? Well, then this time r, you'll notice it says 1 minus r this time. 1 minus r is a decay form of this. And r is the decay rate. just like it was the growth factor over here. It's the decay rate over here. I'm sorry, the growth rate over here. It's the decay rate here. And 1 minus r, the whole term, 1 minus r, is called the decay factor. Also go to the point 0a. Okay. And there's something else here too. You'll notice that I have a dotted line down here at y equals 0. And what's important to understand is that's called a horizontal asymptote. All exponential graphs have a horizontal asymptote. Every single one of them has one. Okay? It defaults at 0, so y equals 0 is where all the parent functions, where they all kind of default to start. Some graphs will move it, but for right now, it's going to be at y equals 0. How do I know if it's going to move? You'll see a plus or minus number after this expression. So it'll be this thing right here, plus a number, or this expression right here, minus a number. If you see that, then this horizontal asymptote will go up or down accordingly. But for right now, it's at 0. Most real life problems are going to be at 0. So that's what we have right now. In the future, though, know that it will move. Now, what is a horizontal asymptote? A horizontal asymptote is a horizontal line indicated by the dotted line y equals 0 up here, where the y values of the graph will get closer to it as the x values go extremely large or extremely small. So in this particular case, as x gets larger, okay, as I move out farther and farther and farther and farther, this y values are getting closer and closer to the line y equals 0. So much so that if I go out far enough, it'll look just like y equals 0. In this one, the x values have to get really, really small. So I'm going this direction, so the numbers are getting smaller, and the graph is getting closer and closer to the y equals 0 line in this direction. When that graph does that, when the graph gets closer to a horizontal line, the farther out I go, that line then is called a horizontal asymptote. Okay? We say the graph gets closer to the horizontal asymptote. That's what we're talking about. Now, some people say, right now when you first learn this, you'll notice that this graph right here will not cross the horizontal asymptote. But just know that that is not always true. Graphs can cross a horizontal asymptote. The only stipulation for a horizontal asymptote is the farther out I go, the closer the y values get to 0. That's what makes it a horizontal asymptote. Okay? These graphs, though, exponentials, do not cross the horizontal asymptote. It is like a boundary line. It will get closer to it, but exponentials do not cross it. Okay? Nope, and that's what I just said right there. Some graphs allow the y values to cross the horizontal asymptote, but the exponential functions do not cross theirs. So they will get closer, but they will not cross. So, how do I graph? Now, your graphing is going to be pretty straightforward. It's very simple. But as you move up in the family of mathematics, it can get a little bit more intense. So I gave you basically the process that you're going to follow from this point forward. For you, it's very simple because the middle point is not going to change. So what you're going to do is you're going to make a table with the 0 in the middle. So this is the part that will modify as you move up in mathematics. So right now, you're going to make a table and you're going to put 0 in the middle. And you're going to pick 2 numbers that are bigger than 0 and 2 numbers that are smaller than 0. Okay? If I'm graphing an exponential function. If I'm graphing real life problems, I have to go based off of what's feasible to plug in. So if it's not possible to plug in a negative value, then I don't. I only plug in numbers that I can plug in to match the context of a problem. You're going to draw your horizontal asymptote as a dotted line. You want to label that also. Then you're going to graph the table and draw the curve. You want to label the center point and one other point. So I have an example here I'm going to do for you. Here is y equals 3 times 2 to the x. So we're going to graph that. So first off, we have to make a table. So here's x, here's y. We're going to put 0 in the middle because that's the number that makes the exponent 0. That's why we choose that number. This middle number is the number that makes the exponent a 0. And then we pick two numbers bigger than that, so just the next two integers, and two numbers smaller than that, the next two integers that way. We're going to take these numbers and plug it in and get a y value that goes with it. I always start in the middle just because I know that one's the easier one. If I plug in 0, then I get 2 to the 0 power, which is 1. And 1 times 3 is 3, which confirms the fact that this number should be the y-intercept. Now, some of these we want to do on scratch paper on the side. So if you can't do this, then you do this process. I'm going to plug in a 1. So this is 3 times 2 to the 1. 2 to the 1 by order of operation. Remember, do PEMDAS, please excuse. We got to do exponents first. So this is a 2. 2 to the 1 power is 2. So I get the number 6. Do it again for the squared. So this becomes 3 times 4. 2 squared is 4. So this is 12. And then we do these over here, the negative ones. 3 times 2 to the negative 1. Well, a negative exponent makes this flip over itself. So this becomes 3 times 1/2, or 3 over 2. And then we do the next one, 2 to the negative 2. So this becomes 3 times 1/2, and then the exponent turns positive. When you flip it over, the exponent turns positive. This was a positive 1 up here. And then 1/2 squared is 1/4. So this is 3 times 1/4, which is 3/4. And we write that in there. And you'll notice, yeah, if you kept going, you will notice that this thing is going to get closer and closer to 0. Okay? See how the numbers are declining down and they're getting closer and closer to 0. This is a growth function, so I already know it's going to look going up like this. Okay? So we draw our graph, use graph paper as best. We extend our horizontal asymptote, which for right now will be at 0. Put in some numbers in here. I don't need too many because I only went out to 2. I do one more than the table does just in case I need to show that the curve properly. So this is 12 up here. One, two, three, -1, -2, -3. And then you just put your dots in here. So 0 goes to 3, 1 goes to 6, 2 goes to 12, -1 goes to 1.5, -2 goes to 3/4. And so I know by the shape of this, it's going to come down this way. Okay, so I don't need to do any more dots. I just need to draw the curve that goes through these dots. I usually turn my paper around and do it like this. So I usually just make sure I plant the heel of my hand. Okay, but I want to make sure that I can, by just turning my wrist, that I can hit all the dots. Okay, if I can, then I can just follow this line, nice and smooth, start coming up to hit all of these dots. And if you don't move your wrist, you will actually go through all the different points. Can't really see all that, but just by doing that, I can draw a nice smooth curve. See how I'm just moving my hand? And it will go through all the dots. Okay, but when you put it, you should be able to touch all the dots with your pencil just by moving your hand, not lifting up your wrist, and you should get a nice smooth curve. Put an arrow on the end. Make sure you draw it all the way out so it's getting closer to the horizontal asymptote. You want to make sure it's going almost very steep when you get at the end here. You need to label 2 points. 1 point is the center point. And then one other point. It doesn't matter which one you pick. Usually I just do the next easiest one. And there's your graph right there. So this is how you want to graph. You'll need to practice this, obviously. But there you go. Okay? So the next thing you're going to be asked to do is some word problems associated with exponential functions. And I'm going to give you the first one, and then other ones we will do, like growth and decay function stuff, we'll do in class as we do homework and stuff. So this one I need to talk about. This is where money investments earn their interest, income, and stuff like that. This is called compound interest. It is a formula. In Algebra 2, you do this formula also. In Algebra 2, I require them to memorize it. I will not require you to memorize this formula. I will just require you to know how the numbers go into the formula. So here's the formula, compound interest. Now here's what all the letters stand for. So the A stands for the amount of money after you compound interest. P is your principal, and the principal is the starting amount. If you look closely, you'll see some very similarities to the exponential growth function. Remember the 1 plus R? So this right here is a more fancy version of that. Because this is compound interest, it's a little bit more involved. So R is your yearly interest rate. And this is the key, as a decimal. Many people get this wrong because they forget to change R to a decimal, because it will be given to you as a percent. T is your time in years. And then the N, in this particular problem, stands for the number of times per year that interest is compounded, which means calculated. Okay, how many times are you going to figure out your interest that you earned? So that's how all the numbers, the letters represent. That's what they represent. And so let's go do a problem. Okay, and I'm not going to write out the problem. I'll just show you the problem, and then I'll show you the work that goes with it. Okay, so here's the problem. So I'll read it to you, see if you can read it here. So if you deposit $1,000 into an investment account that pays 10% annual interest, and you do this on your 18th birthday, how much money will be in the account on your 68th birthday if interest is compounded quarterly? Okay, so this is kind of like an investment thing. So let's go figure this out. So here we go. So the first thing it says, I deposited $1,000. So that means my principal is $1,000. And an account that pays 10% annual interest. So that means R is 10%. But remember, R has to be as a decimal. So 10% as a decimal. Remember, just move the decimal point 2 places. That is 0.10 as a decimal. So the next thing I have here is, what is the time? Well, it's your 18th to your 68th birthday. So that is 50 years. So your time is 50 years. Okay? So the only thing left is to figure out this N. What does that mean? Well, if you remember, the story said that it was compounded quarterly. This is usually how investment accounts occur, is quarterly. So quarterly means 4 times per year, because there's 4 quarters in $1. Quarterly means there are 4 quarters in 1 year, so N would be a 4. Okay, so our job now is to take this information and plug it into that formula right there. Make sure you do it carefully. I'm trying to find the amount after. My initial principal is $1,000. This is 0.10, and this is a 4. Up here at the top is 4 times the number of years, so this is going to be 4 times 50. Okay? And so at this point, we just use a calculator. Okay? Let me get my calculator. So, type it in as you see it. So 1,000 times and then I have 1 plus, and then a fraction. The fraction is 0.10 over 4. And then I'm going to raise that. Now, I'm not going to type, I will. 4 times 50. So there it is typed in. Control and enter gives me a grand total of 139,563.89. So that means your $1,000 investment will grow to $139,563 roughly in the course of 50 years. So that's a pretty good investment right there. So that's what you're going to be asked to do using this formula. Again, I'm not going to ask you to memorize the formula. I will give it to you on the next test. This will be a test question. But you need to know how to find the numbers and plug it into the formula correctly. So more examples will be done in class. And there you go.